Okay, so now we're going to continue with talk point 7, triple integrals in spherical coordinates. Right? So it's just, again, another way to locate a point. It's a whole new coordinate system, sort of like what polar coordinates did for 2D. Now they're doing one for 3D that deals with angles and the distance from the origin. So the setup is the following. You want to locate a point in 3 dimensions, so it's something like here. So here's what you're going to do. You're going to measure the distance from the origin to the point. We're going to call that distance rho. Right, that's what they call it. Right, if you figure out the point right below that point, its projection in the xy plane, connect that to this. This is the familiar r from polar coordinates. We're going to have the angle theta, which is the same angle from polar coordinates, measuring around to that line. But we have a second angle now that starts at the positive z-axis going down to this line. That angle we call the angle phi. Okay? So if you give me these 3 numbers, rho, theta, and phi, I'd be able to locate a point, right? Tell me what angle I move around in the xy plane to get right under the point. Tell me the angle I have to come down from the positive z-axis, then tell me the distance I have to shoot out. And that will allow me to hit the point. This is called cylindrical coordinates, because really it's spherical coordinates, because really it's sort of locating things based on how they would end up on a sphere. And so you sort of imagine that there's this sphere here with radius rho, and you're trying to figure out how to navigate throughout that sphere. And we'll see this sort of coordinate system is very convenient when you are integrating on a part of a sphere. Right, just like how cylindrical coordinates was very convenient when you're integrating on a part of a circular cylinder. This comes in handy when you're integrating on a sphere, or a part of a sphere. Do you have a question?
So is Greenwich? No, never mind. I was going to make that. So you could sort of think of them as latitude and longitude, almost, phi and theta? Or theta and phi, respectively?
Almost, yeah.
Okay.
Yeah.
Yep. Where your theta is in the equator of the sphere of radius rho. Yep.
So this is just in case of sphere?
It's most convenient when you're doing a sphere. Just like with cylindrical coordinates, you can really set it up whenever you want. It's usually not convenient in most cases, right? We're going to have a set of equations that is associated with this coordinate system, where you're going to see that it comes in handy sometimes. So back in cylindrical, we realized that the expression x squared plus y squared was really convenient. So if we saw that, or we saw the region projection was a circle, it makes things work out nicer, right? There's going to be a bunch of situations where this makes things work out really nice, right? And we're sort of going to examine those situations now. Notice here, this can form a right triangle, that's r, this is your theta. If that's the right triangle and this is phi, could you tell me what r is in terms of the other variables I just introduced?
R sine. Oh, sorry. Phi.
Rho.
Sine. Or rho sine. Phi. Sorry.
No, 10.
Rho sine 90 minus
Well, r I can sort of project, it's going to be the same thing here, right? And then sine of this is opposite over hypotenuse. So in other words, I could derive that r is actually just rho sine of the angle phi. In which case, since x equals r cosine theta and y equals r sine theta, this would mean x is rho sine phi cosine theta and y is rho sine phi sine theta. Right? So they sort of get a little bit longer. So when you're talking about in spherical coordinates, x is not r cosine and r sine anymore. It's rho sine phi cosine theta and rho sine phi sine theta.
This is not the same row as rho for density, is it?
No, it's not the same rho as rho for
Okay.
density. Right? So your rho here is just thought of as the distance from the origin. It's completely different from density. It's just a coincidence that they use the same variable.
It's the distance from the origin and the
It's
z.
the distance from the origin
and
to the point that you of consideration.
Okay,
So it's distance from 0, 0, 0 to hit the point.
okay.
Right? Always the distance from the origin. Just as how in the xy plane, r is the distance from the origin to the point on the curve. It's the same thing, except now
It's
you're
in
not
3
stuck in the
space.
2 space, you're stuck in 3 space. So your rho can actually go above or below the xy plane. Right? So
And it can
that's-
go totally around it as well.
Yes, the theta controls, the theta is what can get you around anywhere. And then the phi
And then the
can get
phi
you
gets you-
above or below the xy plane.
Okay.
Right? So that's going to give you a maximum range for the phi, which is 0 to pi, and I'm going to tell you all these first, but later, but I want to get to the equations now. What's the other equation I should tell you? How would you find the z value, right? Because this is,
That would depend on rho.
Is that one? Is that something?
right? Where's the z? Here. It's just the height above the xy plane, right?
Right.
So this is z. How can I write that?
Cosine, rho cosine phi.
Okay. Using SOHCAHTOA again, we get z is equal to rho cosine phi. And is there going to be some sort of... So, so I sort of summarized how this coordinate system works. We have those equations. X equals rho sine phi cosine theta. Y equals rho sine phi sine theta. Z equals rho cosine phi. And it actually turns out that rho squared is equal to x squared plus y squared plus z squared. Right? Which you can check with calculus yourself. Well, not calculus, you just square this expression, square that expression, square that expression, add them all together, the result will be rho squared. So now this is a very convenient expression to have, which you might notice is just, it looks like a circle centered at the origin, a sphere centered at the origin with radius rho. Right? So it's really set up to encapsulate the idea of a sphere. So that's why it's very convenient when you're using it for a sphere. Let me just make some notes on the angles theta. It's no same angle from polar coordinates. You don't really think of it any differently. Rho. This is the distance from the origin to the point. Theta is the angle OP. I call the origin O and the point P, then your P would look like this. The This is the maximum phi will ever be, no matter what. Phi is always going to be an angle between 0 and pi. I mean, you can fudge things with theta a little bit from like minus pi over 2 to pi over 2 and all sorts of stuff. But phi is always going to be between 0 and pi at some point. And with phi equals 0 at the positive z-axis, and phi equals pi on the negative z-axis. So a new way to locate a point in terms of two angles and a distance from the origin. And we have these equations set. Yes?
So what do you do if on the other side it's on the negative y-axis? Because it's between 0 and pi.
Oh, the theta would swing you around, right? So if you're like in the xy plane, let's say you have a point like behind the xy plane down or something like that. Like your phi, you wouldn't have to measure it all the way like here. You could easily measure it on this side and just let the theta be the one that swings you around, right? So the theta can control anywhere. The phi only needs to go from above to below. It never has to go wider than that. Because the theta can swing you right around to the other side if you ever need to get there.
Professor,
Yes?
the R and the rho, can their values be the same since they're like from the center to the circumference, both of them, right? Can
If
they-
you fall on the diameter of the sphere,
Right.
then yes, they could be the same,
So in
but only in
general-
that case. And generally it won't be, they hardly will ever be. That's if you're in the xy plane, that's the only time they'd ever be the same. But when you're thinking of spherical coordinates, you forget about the r, right? We use the r to derive this and we're done with it now. When you're in spherical coordinates, there is no r. Rho, theta, and phi. Let's do some changing coordinates just to get used. Did I do? No, I did representing surfaces. So we did this back for cylindrical, now let's do a couple in polar. Sphere. Let's say it's something like x squared plus y squared plus z squared equals k squared. What would the equation of that be in polar coordinates? In spherical coordinates?
Rho squared equals k squared.
Right. You'd say rho squared equals k squared, which means rho equals k, right? So a sphere, which is a function of the sum of three squared variables, is only just a constant as far as spherical coordinates is concerned, right? So anytime you're on a sphere, you just think of it as rho equals a constant. That's its equation, right? What about... What is, let's say I said phi equals a constant. What is that? It's a cone, right? This is a cone if it's always a cone. Right? So for example, this would just be the set of all points where your phi is a constant angle. Right? This is phi equals k. Right? But that would mean you would include all points going around where you'd always measure the angle phi equals k. You'd end up with a cone. What is theta equals k? Right, this is a plane. Through the origin. And it's orthogonal to what?
To phi.
Orthogonal to the xy plane. Right, so this is like so if you measure your angle theta here, you want all points that have that angle theta from the positive x-axis. Well, that would just define a plane. Right? Okay, just going to use that. Also, let's look at the basic differential unit. That's going to be important when we get to integrals. So let's say our origin is right over here. We're measuring points going out there. Right. That would be what the basic differential unit looks like. This is going to be the delta phi. The change in phi is what would give you the height of this unit. The change in theta below, if you project this down, you get a rectangular part where the change in theta actually gives you that. So the length of this is actually the change in theta. The change in theta happens here. We're going to be figuring out these guys. So this is the change in rho going from this point to that point. How would I figure out the height? Like this one.
One. Delta.
It's the arc length. Right. What's the formula for arc length?
Equals theta r.
Do you remember? Yes, S equals R theta. So remember, if you have a circle and theta, oh, let's use phi here, and let's say instead of R I call it rho, then the length of this would be what? It'd be rho theta, rho phi, right? This is the arc length formula. Which means the height of this guy here is actually rho times d phi. And
The
this
height of which guy? I didn't see your hand.
This right
The
here.
height of that, okay. Yeah.
Okay? The length of this is just the change in rho. You went from this distance from the origin to that distance from the origin. And then the change in here is going to be what?
That would be the change in theta, no? Am I looking at it, am I
Well,
looking
you
at the
can look
top
at it
or
as
the bottom? The side or the bottom am I looking at? Yeah, it's the bottom, it's delta theta.
Yeah. And so your delta V is going to be equal to, actually, no, this is actually rho d, rho delta theta, by the same arc length argument, right? So this is going to be, the volume is just going to be length times width times height. So this is going to be rho squared. This is actually something else. I'm missing something. What's change in rho? No, I'm measuring this length here. Not this one. I was just drawing it on the inside. It's a bad sketch. This is probably why I'm missing something. Let's see.
Well, that change would be delta theta. Because it's the same point on rho for the whole thing. You're
Right,
just
but
moving sideways.
it's not just yet. It's going to be a delta theta, but remember your theta is in the xy plane.
Right.
Which means I'm applying the arc length formula. However, I'm actually applying it in the xy plane. Right?
Right.
Which means my radius now is r.
theta.
So this length that I'm looking for is actually r delta theta. But my r I know is what? Just rho sine phi, right?
Right.
Okay, so that's actually the right thing. So now here, if I multiply this by that, I would actually get rho squared sine phi delta rho delta phi delta theta. This would imply, by the way, that for integrals, dV would actually be rho squared sine phi d rho d phi d theta after applying the typical Riemann sum, which gives us finally the formula for integrating in spherical coordinates. Triple integral over a solid of f of x, y, z, dv is equal to, okay, hold your breath. Everywhere you see an x, you're going to replace with rho sine phi cosine theta. Everywhere you see a y, you're going to replace with rho sine phi sine theta. Everywhere you see a z, you're going to replace with rho cosine phi. Then your dv is actually going to be rho squared sine phi d rho d phi d theta. I'm going to just write e here. The limits would be obvious. Theta is the same old limits that you're used to. Then phi is going to be, you're going to find out the limits for the angle phi, then you're going to find out limits for the angle rho, and right? But the difference is here, something you always have to remember is this guy, right? Just like how in polar coordinates you had that r that you always had to just put there, r dr d theta. With spherical coordinates, it's this guy, rho squared sine phi. Every time you said something with spherical coordinates, you have to throw that in there, right? And it's because of how the volume unit changes according to the arc length formulas. let's actually do some examples with this. The general formula is scarier than it looks. I mean, the general form for cylindrical coordinates looked really scary, but you'd see when you were applying it, it wasn't that bad. Let's do an example.
Actually, it's not that bad.
Well, that one's actually not that bad. That's still the ice cream cone, but an example like this is going to be a good example when spherical might be handy. Okay, did we try this one? So what's this? It's a what?
Sphere.
It's a sphere. What's the radius? And the center is? This guy you can write as x squared plus y squared plus z minus 1 squared equals 1. If you just bring over the 2z and complete the square. So that's a sphere. The center is actually 0, 0, 1, and the radius is 1. So the sphere actually sits on top of the xy plane, right? So it's not exactly in the center. Which means if you tried to set this up using polar coordinates, you'd have a little bit of trouble. So that's your sphere. The center is 0, 0, 1, so it goes down to 0. It goes up on z, up to z equals 2. And then we have the full familiar cone. This goes up like that. And it's a square, so it would also go down like that, but we don't really care about the bottom. We want inside both, so really it's this ice cream cone. But now your ice cream is given by a sphere that's above the xy plane. Just curious, what would be the equation of this sphere in cylindrical coordinates? Cylindrical. That's the one with polar.
R squared plus z squared is equals 2z.
Okay, so how do you simplify? Like, what would you put on the limits for z, the upper limit? What would it say?
It's gonna be this thing, which is
We solve for z, right?
Yeah, you'd solve for z.
1 square root of 1 r squared plus 1.
Yeah, this would be z equals 1 plus the square root of r squared. 1 minus r squared. Okay. And that plus sum would make things a little bit more, not totally, but does. Okay, so now we want to set this up. We want to do it in spherical coordinates since we're in the spherical coordinate section. So we know that we're going to want volume to be the triple integral over this solid of 1 dv. Now, if you were doing that, what would it look like? We need to figure out what is rho, what is theta, and what is phi. Well, theta should be fine, right? Because if you look in the xy plane, what's going on? You have this a full circle. So theta is that 0 to 2 pi. But what is rho? Rho would be the distance from the origin to the sphere, right? it's always to the most outer reaches would be the sphere. You're really measuring the distance to the sphere. How
So
do
would you
measure
use
that
an arc?
distance?
So, 2 cosine phi if you plug stuff in or do algebra.
Well, rho is the distance to the sphere.
Right.
So look at the sphere, right? Now what is the sphere's equation?
X squared plus y squared plus z squared equals 2z, so rho squared.
Right, so that just says like x squared plus, let me write it, x squared z squared equals 2z. So this would mean rho squared is equal to 2 rho cosine phi. In other words, I can say my rho is equal to 2 cosine phi. So my rho goes from 0 to 2 cosine phi. And what's the phi?
It's pi over 4, right?
Phi goes from 0 to pi over 4. How did you figure that out?
It's the intercept.
Phi would be the angle that goes from the positive z down to this cone, right? That would be the angle phi.
And I just got it from the equation, the cone.
You could do it that way, so I should probably mention this. Run out of space by the time I figure out how to do these limits. All right, so now for phi, several ways. Use the equation of the cone. So this says z squared is equal to x squared plus y squared. This would mean that rho squared cosine squared phi is equal to rho squared cosine squared theta sine squared phi plus rho squared
Sine squared theta.
sine squared theta sine squared phi, which is just rho squared sine squared phi, right? Because I factor that out and I get cosine squared theta plus sine squared theta, which is 1, so I'm left with that. So it's just rho squared cosine squared phi, which means that I need cosine squared phi to be equal to sine squared phi, which means that your theta can be plus or minus pi over 4, right? Because that's where cosine and sine have the same values. But I know that I want the positive because, like I said, I only need to go between 0 and that. So take b equals pi over 4 to get to the cone, and so I know it goes from 0 to pi over 4. Another way is to actually look, if you look at the floor-like xy plane. Here's your z-axis pointing up, and you wanted to do, all right, so this is the cone. Right, this is x squared plus y squared equals z squared. What you notice here is that z is the height, right? It's the distance above the xy plane, but it is also the radius, right? If you look at this as a circle, x squared plus y squared equals z squared, it looks like a circle with the radius is z. So really, the z measures this height here. It also measures this distance here. And so if you have to figure out what phi was, tangent is opposite over adjacent, so tangent is just 1, your phi would be pi over 4 that way. And it's just something you can always memorize from this point on. So if you see z squared is equal to just x squared plus y squared, or z is equal to the radical of x squared plus y squared, you know that your phi is, the maximum range is pi over 4. So for the standard cone, that's going to be your phi. And if they ever tweak it in some way, like they could say z squared equals 2x squared plus y squared, right? Or x squared plus 3y squared, then you just go through one of these methods again to find it. But that's if they're really mean. The standard one, the standard cone is this one, which your phi is 0 to the power of 4 for the top part. Okay. So with that in mind, so we have v would be equal to 0 to 2. 0 to the power of 4. So it goes from 0 to 2 cosine phi. 1, our dv, though, would be rho squared sine phi. Okay, how do I do that one? Integrate with respect to rho first, what do I get? Huh? Rho cubed over 3. And go between 0 and 2 cosine phi. I have to put the fundamental theorem calculus first. I have to plug this in here. So I would get 2 cubed, which is 8, cosine cubed phi sine phi. Phi d theta. By the way, there's no thetas in this. I could just actually use that as 2 pi. And then what's the integral of this? What's the integral of cosine cubed sine?
Wouldn't that be cosine and then the double angle of cosine squared? Instead of cosine squared, 1 minus cosine 2.
No, couldn't get too hard. Substitution. Substitute what?
Cosine is u.
U equals cosine, your du would be minus sine, right? So this is just actually minus cosine to the 4th over 4. And then, so this 4 is going to kill that 8, get 2. So we have 4 pi over 3 times, if I plug in power of 4, I get minus, what's cosine power of 4 is what?
Root 2 over 2.
Right, you can think of it as 1 over radical 2, or root 2 over 2, we raise that to the 4th, plus cosine 0 is 1, so this is 4.
Did you do the
Huh? Come again? Sorry, this is 1. Yeah, because I moved this 4 out. Yeah. So that's actually, this is going to be a quarter, right? And then this is going to be 1, so it's 1 minus a quarter, that's 3/4, and so that would actually just be pi.
Lemon?
I have a question.
Yes.
We could do this in the cylindrical.
You could have done it in cylindrical, yes. In cylindrical, what would it be? And this would be r d z d r d theta. For r. Right, so it would be where they intersect, which you think is 0 to 1. I think it was 0 to 1. Yeah?
From R to
So it would be the cone R2.
1 minus.
This would be 1 plus the square root of 1 minus r squared. In this particular case, it would have been probably easier to do that. Unless you see this. Unless you see this right away. To do the easy way, I was doing it as an example. Like here you have a choice though. Because people do these things, you know, force you to use spherical.
But you would never do that to us, right? You love us too much.
I do it on Ahmed's paper. Okay, what if I gave you the choice? So let's actually look at what T1 and T2 look like, right? Let's say I'm doing T1 and T2. How would T1 look? So what do we have here?
A downward pointing cone.
It's a downward opening cone. Right? So we just have the bottom part of the cone. Okay, and what else?
Sphere of radius.
Sphere of radius 1, centered at the origin. And what region do I want? It's above the cone, but inside the sphere, right? So really it's right? So it's above the cone, but inside the sphere. Okay. What does T2 look like?
Upward opening. No. Downward opening cone.
It's again a downward opening cone. Mm-hmm.
And infinite cylinder, radius 1.
Let's see, it's above this, below this, and inside this. So there's a cylinder coming up here. There's radius 1. Okay, so this is this. Now which region do I want there?
Inside the cylinder, outside the cone.
And below the XY plane.
XY plane.
So it's actually, I want everything around here. Now, set up those two triple integrals. And which coordinate system would you choose? Choose what? So if I'm setting up T1 of that thing, which coordinate system would you choose? And then once you choose it, how would you actually execute it?
spherical?
You use spherical here?
I would use,
Why?
Because, well, the integrand would just be a row squared, and that seems rather convenient. And also, I think I see my way to representing the cone and sphere and all that.
Oh, so that's your only reasoning? Because the T2 also has x squared plus y squared plus z squared.
Yeah, but it's because then it can be
Oh, well, yeah, and also T1 you have sphere, T2 you have cylinder, so.
Well, that's a good way to hazard a guess. We'll have a sphere here and a cylinder there, spherical and cylindrical. Yeah, that's sort of one way to go. If I wanted to set up, let's say I didn't see that, and I'm just like, I'm afraid of spherical, but I wanted to set up cylindrical here, what's the problem I would end up with? I would end up with a problem in Z. How? What would the intersection here be? The curve of intersection. It's going to be some sort of circle, right?
Yeah.
What would that circle be?
the radius.
Yeah, what's the radius?
Or,
1 over root 2. So that's going to be, if I project it up to the xy plane, there's going to be, the radius is 1 over radical 2. Right, so now, if I'm setting up that in cylindrical, right, I'm going to have, this, first I'm going to have r squared plus z squared times r dz dr d theta, right? Now theta is pretty okay, that's just 0 to 2 pi. R is also okay, that's just 0 to 1 over radical 2. What are my limits for z? There's no plane. What plane?
I guess on the bottom you have the cone, right? And that's z equals.
No. You have to take everything outside the cone, on the outside intersection, is a sphere. That's the bottom.
That's correct. If you look here, look at
You're right, okay.
look at that.
Right, okay, because the,
When I'm inside the cylinder radius 1 over radical 2, the top is my sphere, the bottom is the cone.
right.
But it's possible to be outside of that, in which case the top would be the sphere and the bottom is also the sphere. To set this up with cylindrical, I'd actually need 2 triple integrals, right? One with 2 top and bottoms. Right? So if you try to set this up with cylindrical, it's possible, but you'd work a lot harder. Right? Because your top and bottom actually changes
You'd have to
outside
chop
of
it
it.
up into different.
You'd have to chop it up. Right. Whereas so spherical is the way to go. Now if we wanted to do it in spherical, what is the way that this would go? And we can do it in one triple integral here. What's your phi, which is from the positive z-axis down to here?
It's going to be, the bottom is going to be negative pi over.
And we only think that this is
No,
where
that's
t
the
equals
positive.
0, opening in the positive.
Right, so that's pi over 2 plus pi over 4 is 3 pi over 4?
Yeah, or you know that here was pi over 4,
Yeah, that's what I'm trying.
and so all of this was pi minus pi over 4, so you can just take that to be 3 pi over 4. So your theta is 0 to 2 pi, this guy is 0 to 3 pi over 4, and what's your rho?
that would be the distance to the, no.
0 to 1?
0 to 1, distance to the sphere.
Yeah.
0 to 1, the integrand x squared plus y squared plus z squared is just rho squared, And then you times that by rho squared sine phi d rho d phi d theta. Right? So you end up with a single triple integral and the limits are all constants, whereas you'd end up with you'd end up with two triple integrals where the limits on the z would have to be functions. Right? So in this is one case where you see that spherical actually does help you with it. And so that was the setup for that. About T2. Okay, so now we go over to T2 and sort of examine this one. How would T2 work? Well, cylindrical would probably be the way to go.
Wait, so did you say that we cannot do that, like one spherical and one cylindrical?
No, I said use coordinate systems of your choice.
Oh,
So you should choose the better way to do it. Cylindrical is a pretty nice way to do that. How would that look in cylindrical?
And in 0 to 1?
Huh?
0 to 1.
Yeah, 0 to 1, right. It's just, this is going to be the region of projection. So 0 to 2 pi, 0 to 1. What does your z go between?
Negative square root of, wait,
What's the bottom part?
oh, it's,
The bottom is the cone, right?
right, so yeah, so negative square root of x squared plus y squared,
Which in
To
polar coordinates
0.
is,
which would be negative r
so it's just minus r
to 0.
up to 0 of, now x squared plus y squared plus z squared, that's actually r squared plus
So
z
z
squared.
squared,
And then I have
r,
r dr d theta. dr d dz dr d theta. If you were to try to set this up using spherical, what problems would you end up with? If you're measuring the distance from the origin to the outer part of your solid, you'd be measuring the distance to that, to this,
you'd have to have
the
two
cylinder actually,
sets of
right?
integrals.
Which actually changes, right? It wouldn't be a constant anymore. Because to get to the lowest part here, you're actually along the hypotenuse of a right triangle. By the time you end up here, you're along the base of a right triangle, which there's no telling that they're the same. And of course, if you're in the middle, neither of those lengths would work. So your rho is actually a function here. Right? You'd actually have to figure out what is the distance, a general formula for the distance here. And so you know if the distance measured here is rho, and that would, the distance here would actually be phi plus pi over 2. Right? You're going to have to use like trig to figure out those limits, which is, it's dual, but it's sort of annoying. All right, so this one, I would opt for the cylindrical way to represent the
So basically, if I was sphere, use a sphere, if it's a cylinder, use a cylinder, right?
Almost. I mean,
The moral of the story.
there are ways it could make it nasty. Like if I didn't put a z squared here,
Yeah, but we would.
then that wouldn't be a rho squared. That would be a rho squared sine phi cosine and then the mess you'd have here, it might be easier to do two triple integrals instead. It really depends on the problem.
And how nice you're going to be to us, right?
But it depends on the problem, that'll be a problem. Problem in itself.
Okay, so now I have a quiz for you guys. Just a handout. Here.
Well, we actually have sheets of paper.
Oh, it's not give this to you. You don't need it. It's going down.
Oh.
Yeah, so in series we're going to be doing
Can we get
convergence tests,
Are you serious?
and in
Can you make this question hard?
in the Stewart text that we have, they don't have a table like this that has all the tests on one page. So I thought I just copied this from another textbook. Who's missing?
Wait, so are we done with this chapter?
Yeah, we're done with 12.7. So now the next part is we're going back to chapter 8. to
I have
do
a question.
series. Yes.
Can we have the chapter 8 homework due after the exam?
Oh yeah, isn't that the way it works anyways? Because
Yeah, because you want us to focus on chapter 12, don't you?
Okay, so the test on Thursday is for chapter 12.
And
then
13.6?
The following Thursday is the test on chapter 8, and then the Tuesday after that is the final. Yep.
It also includes 13.6.
It includes 13.6, yes.
So is that a yes? Can we,
No, that would be good.
Yeah, so the test on Thursday is 13.6 and chapter 12. Everything we did there, with everything with integrals.
Can you make the
Basically.
question easy?
No.
No, you
Well, I might make a Mets question hard.
No, you don't.
can, so
Do.
Javon, can we hand in the homework for 8 after the exam?
Probably, maybe.
I think we'll stop there today because
Thank you.
it's kind of long. We're not going to get anywhere.